everybody for the opportunity to come and speak to the IoT group. I've come to be a little bit fond of this group. My co-presenter today, Copeland, actually I met through a contact here a few months back, and we sort of hit it off, and turns out that we've got an emerging, a still establishing business relationship, and we're working on some exciting things together. And he, a little bit later in the presentation, will give you a little bit of update on what we're doing together. Topic of today's presentation is rapid chip development for the IoT space. And when I think of IoT, Avnet does a lot of great things. There's a huge number of catalog parts that are here to help you with your IoT designs that they can help you with. And oh, by the way, if you haven't talked to Will yet, he's looking for sales guys. And he'll be happy to help you with that. But one of the things we'll be talking about in this presentation is really the emerging needs of IoT and why catalog parts don't always cut it. And some of the things that really are going to have to be incorporated into new devices that are going to require new chip designs or new FPGA developments that are incorporated in a product. So we'll talk about that. And then we'll talk about what we're doing to help make that more affordable, less risky, and really accelerate the time to market to make that a viable option. So let's get started with the question. All right, so the question I'd like to start is, why do developers think that custom silicon is not an option today for product development? I mean, when someone thinks about new chip development, right away you start thinking, well, that's going to be too difficult. I don't have the expertise, or I don't have the money, basically. It's going to be way too expensive, right? Or maybe it's going to take too long. I mean, some chip designs can take a year or even more to bring to market from the time of conceptualization. Or the risks are just too high. By the time I get my silicon, or and basically designed in my product, the market opportunity might already be gone. So what can we do to change that? What if anybody who can basically design a chip onto a PC board could define and actually create a new chip design and begin simulating? And what if they could do that, let's say in a day or a week, rather than in months or a year? What if we could reduce the cost of developing a new custom semiconductor device by half or even more for an FPGA development by leveraging off IP reuse and incorporating automation? What if you could do it in less than half the time? In fact, in an FPGA, what if you could get there within a week or so? Would that change things? And how does that affect your risk? The time to market, the cost, the expertise in getting the talent risks, or the market success risks? I argue that if you could address those things, the bar is lowered as far as considering custom silicon solutions. And that's what Concertal Systems is working to make as a viable option. So what would it mean to the different emerging markets? I mean, these are all somewhat related in some ways, whether we're talking IoT. We'll hone in on that a little bit more, but what about autonomous systems, driverless cars, drones that need to swarm together and collaborate with each other? The 5G space is going to enable a lot of applications of localized collaboration of different devices that don't require a central master control mechanism to make it happen, to make them work together. Machine learning. We're putting all these devices out there. We're generating a lot of data. We're going to have to collect that. And Ryan, for instance, with Citadel, that's where his expertise is, right? And we're talking about ways that we can basically work with them in order to incorporate machine learning and solve some of those problems with the IoT devices. Artificial intelligence. There's a huge amount of stuff that's going on in the cloud today, whether it be Google, Amazon, or others. But that's moving to the edge. As 5G comes along and things have to work more autonomously, and they have to collaborate in a more localized way, AI is moving to the edge, right? It's not all going to be done on some centralized system anymore. Security. Boy, let's see, 50 billion more IoT devices are estimated to be hitting the market in the next 5 years. That's up from about 20 billion today. And those 50 billion devices are going to be more autonomous. They're going to have to incorporate AI at the edge. The whole point is, when you look at IoT, a lot of these things basically are important. Security is a key element. How are you going to solve those issues? They're cost sensitive. Time to market demands on being able to capture these 50 billion new opportunities, right? Machine learning friendliness has to be part of the AI system because you're generating and collecting this data. What are you going to do to collect it and work with analytic companies to do something useful in AI at the edge? It's going to require new silicon. Catalog parts are going to get us a lot of the way there. They have so far. But to do a lot of those new features cost effectively is going to require different devices than you find in most of the catalog parts today. So there's a tremendous opportunity if you can address those needs. So let's look at a little bit of what's happened in the past year. This is a graph of the most complex chips that have gone to market in the last 20 years or so. And we've all heard of Moore's Law. Basically every so many years, 18 months or whatever, the capability doubles on the manufacturing side. Some people say we're at the end of Moore's Law. That is proven not to be true. And even though we are approaching the point where we're doing all we can with process technology, that doesn't mean that advancements are going to stop. We're going to be able to do things like systems beyond a chip, the collaborative nature of multiple devices, for instance. The complexities just are going to move beyond the bounds of the semiconductor packages. So this growth curve is still happening. The problem is, as that has happened, devices have obviously become more complex, but design productivity hasn't kept pace. The tools have improved. They allow us to do this, but the teams that are required to do the larger chips have grown huge, and it's expensive, right? And so there's this productivity gap that exists. And that's where we are. That's where Concertal Systems fits in. We close that productivity gap. If you look at the state of the industry as far as what it takes to bring products to market, there's companies, great companies. Let's take TI, for example. They're the dominant semiconductor company here in the Dallas area, right? I mean, it can take months, if not year or more, for a customer needing to make it on some engineer manager's desk to write an RFQ response. And if it's lucky enough to be picked up, some product definer basically still has to generate all the documentation stuff, goes to a design team, a detailed specification for consideration, basically has to create another gate to move forward. And then, all this time has passed, and then you start design. Maybe. I mean, just the time frame alone to get through that process, most ideas don't make it to silicon. They don't even make it into the chain. And then if a design team picks it up, it can take 5 months or so to create a simulatable new design. And a lot of times the customers don't have access to those simulation models or anything. And it's no wonder why it can take you over a year or so to get to an emulation, basically ready design on an FPGA, for instance. And then not to mention, you're going to build this into an SoC. There's some formal verification you have to go through, not just functional verification, but formal verification to make sure what you end up with, it will actually work when you get the parts and has to be manufactured. I mean, it's a lot of time. New chip designs can take large teams. They can take 1 to 3 years to develop, sometimes even longer. And they can cost anywhere from maybe $2 to hundreds of millions of dollars in order to get that part to market. In fact, the last NVIDIA chip, I think in 2019, cost nearly $1 billion from the time they conceived it to get silicon out to market. There's a lot of room, basically, to cut costs. And what Concertal does is we consolidate the workflow steps through accessible automation technology. We can say millions of dollars to a project. We allow, through simplifying and automating the front-end tasks, a product definer who's not a designer or even a customer himself to simply go to a website, select the functionality they know they want to be part of that new chip idea they need to bring to market to capture their new market opportunity. Customize it, or if they don't customize it, that's okay. We'll just automatically generate a highly configurable design that they can begin simulating right on their web browser. And we'll demonstrate this a little bit later today if there's time at the end. So we can go from concept to actually simulating a design without installing any software or writing any code or having to incorporate experts into that flow in minutes to maybe a week or so, as long as you're leveraging off reusable IP. And if you don't have IP, we basically provide a framework to consolidate and streamline that workflow so you can do that more effectively and engage with IP providers to help fill in those gaps if you want. And we do this all through an easily accessible web browser. If you have a web browser, you have access to our technology today. And we don't have to share the IP for you to be able to try that IP and use it and begin simulating and building a new design. So, the question I have to ask is, what would you do with customized silicon if it was a viable opportunity? How low does the bar have to get for you to consider it? Well, I would argue that we're lowering the bar so much that you can't ignore actual, at least looking at the opportunity. Before, what was just not even an opportunity to think about, it's understood. The risks are just too high. The time to market demands are just too long. The costs are too much. You might not have the expertise. But with what we're able to demonstrate doing today with our technology, it lowers the bar so you can now consider that. We'd love to help to get you there. So if you have an opportunity or you know someone who does, we really want to talk to you. We have two products that are usable today. IntelliConnects is basically our integration fabric. It's sort of an intelligent network on a chip, if you will. And we automatically generate that and customize that for every developer's needs, basically, through the database-driven design flow. And that's actually accessed through our web portal with our Orchestrate SoC tool. You don't have to build a chip to use this. We can take this and you can apply this to rapid FPGA development also. So Carl's going to talk here in just a moment about what we're doing to build an FPGA platform to allow him rapid development of customized motor controllers for his business. And then when the volume gets up, we'll be able to basically accelerate and build SoCs when the time's right. So he's got all that upfront work done, can capture the market opportunities, and we can continue customizing that on an as-needed basis. We can help you with other things too. We can help you acquire IP you might need, design your IP, evaluate the IP, import it, and make sure that it's automation ready with our tools. And whatever makes sense for you, whether it's an FPGA or SoC, we basically lower the bar and allow you to consider that and make it happen. So Carl is going to talk a little bit about what he's doing and basically the partnership we're establishing to help him get there.
Hello, my name is Carl Copeland. I'm founder and CEO of Muse Motion. And last year I had the privilege of presenting to you guys. So I don't know how many were here during that presentation, but I'll give you a very brief synopsis of what we're doing. We have developed a new magnetics that the result is a new high-performance motion system. The photograph you're looking at there on the screen is the world's first paper servo. So we have a new magnetics that allows us to eliminate 85% of the steel normally found in a motor. We miniaturize the steel, fragment it, and miniaturize and optimize the magnetics. And the result is a motor that when you compare it with the same class motor in the servo class, that we're less than 5% the size and weight for the same application performance. In order to do this, we have a very complex design. I don't know how well you can see the image there, but we have over 36 isolated magnetic circuits, 72 poles, 36 isolated circuits that we configure into 3 arrays that allow us, basically we're running 6 3-phase motors to simplify. It's an oversimplification, but we're running 6 3-phase motors on a common shaft. So as you can imagine, that's a fairly complex motor, so we have an equally complex, this isn't triggering, I'll let you do it. We have an equally complex solution for the controls. And actually the motor, you know, I'm a motor guy, I'm a hardware guy, so designing and building the motors, that was the fun part. The electronics way outside my bailiwick. So I'm having to rely on vendors such as Concertal to help me develop so we had to develop custom algorithms. Our magnetics are so new and so different that we actually cannot simulate currently our motor. We have to, all the metrics we've done has been off of an iterative process, which can be fun. So we've actually used those empirical tests to build the data sets that we can then use to build our own custom simulations. And we're actually capturing the algorithms for that and rolling that into our own IP for our hardware, for our electronics hardware and software. And so that's where a partner like Concertal comes in, is as we're iterating, and we're still iterating and optimizing on this new magnetics platform, as you can imagine, with a level of complexity where we're controlling 36 individual circuits and multiple, you know, we have and what I'm not doing justice on is that it's as I say, there's 6 3-phase motors, but they're much more complicated to drive than that. It's a natural trapezoidal wave motor. There's a lot of nuances in the way the inductance and the, you know, all the parameters of the motor operate. And so we really are doing, we have a very complex set of controls that we need to simplify to the point where the end customer is able just to simply send it the same signal they'd send a simple brushless DC motor. And they send that signal, our controls decide what that motion needs to be, outputs that motion to the power electronics, and the power electronics deliver the power to the coils. So that's a very complex system, and so to iterate this level of controls over and over again, especially when it has to be completely custom because there's nothing on the market that drives this motor because this motor didn't exist before. So we can't take off the shelf stock parts in order to do our test fixtures. And so the cost, the financial burden for developing these controls was significantly more than the motor, so which was surprising to me, being a motor guy. So, but in our partnership with Concertal, that's where they're you know, presenting a very tremendous opportunity for me to not only reduce the costs and the barriers on these controls, but to also rapidly iterate. So I like to tell people that we can develop and deliver and iterate motors at the pace of software. So when we're done with our hardware infrastructure, we'll be able to take application requirements and deliver working prototypes in 5 business days. That's unheard of. It's usually 6 months to a year to get a custom solution from a traditional motor company. But well, how do we keep pace with that if we can't iterate the controls and the electronics at the same pace? And that's what the Concertal system allows us to do, is we can go in with our own IP, we can choose what features we're needing for this specific application, and we can take our IP that he was mentioning before about how if you have IP, you can put it into the system, but you can keep it private to yourself. And so we can build our IP space on their platform, and then when we get ready to iterate, we can simply deliver to our end customers a module that encapsulates all of our algorithms that we can keep still as our trade secret, and they simply plug that component in and then build the rest of it. So let's say they're doing a cobot, or they're doing an automated vehicle, or they're doing a drone. So they can take our modules, put them in, once we've licensed them to use them, they can put them into the system and build their system around our technology without us surrendering our IP to them in the process. And it allows us to, once we have that IP in there, to begin to customize, tweak, and augment. And moreover, the FPGA side of it is if we find a board that fits a certain need, that we can get an off-shelf component and then composite that with other electronics. We can build all of that virtually and test and simulate that in a virtual environment before spending a penny on the hardware. And so this rapid ability to iterate the electronics and the software for the electronics at the same pace that we're iterating the motor technology it is a game changer for us. It removes one more obstacle. So now we're able to do the electronics and the motor at the same pace because, you know, a very good friend of mine, one of my advisors and mentors, he was the senior principal engineer for Western Digital for over 20 years. Pretty much every hard drive on the planet runs on his IP. And the thing he preaches to me all the time is like, it's not that the big eat the small, it's that the fast eat the slow. And so that ability to outpace our competitors and outpace the market in the ability to iterate and deliver is a key component. And that's where the partnership with Concertal really comes in. And then we're also talking about the security side of it as well. So, you know, a blockchain and encryption tokens are really key to me for the IoT future because you can have all the data in the world, but if your competitors can sniff it out on the transmission, you're really not, you know, you're giving your competitors your own advantage. So one of the solutions, if you can go back one slide, one of the features that we love is the ability to literally integrate a blockchain encryption between our various components because we're designing our system in a modular way where we have the master controller that's the motion controller, it's the brain, right? All of our motors use the same logic to operate, but the power electronics scale with the power requirements of the motor. And so we're actually able to do onboard tokens to encrypt our communication between the subcomponents and then moreover also do the same level of encryption out of the device through the internet back to our data center and deliver our customers real-time data to analyze and be able to do predictive maintenance, read errors and vibrations on the system because a servo motor is a giant sensor pack, right? It's a two-way communication path. And so that gives us the ability to engage, especially being able to build custom components without having to rely off-the-shelf components. Now we can meet security issue, you know, concerns. You know, we've got a lot of boards that are coming from all over the world that are on-the-shelf products that you don't really know what's built into those boards and how they're being able to communicate back to whomever. You know, we have a lot of stuff being produced offshore, and you would be shocked at the stuff hidden on those boards that are sending copious amounts of data to people who aren't friendly to our ends, right? And so, Huawei being one of the worst, yes. And so, but they're not the only ones doing it. I mean, you've got it coming out of Israel, you've got it coming out of Korea, you've got it coming from people who are supposed to be allies as well. And honestly, we're doing it to our allies. So the ability to, you know, especially if you're working with a government or defense level application, the ability to control the data, and even if someone else puts something on your chain or integrates your product with one of their products, to be able to control that data flow out of your product and bypass even other people's attempt to scrub that data for us is a huge thing because, you know, we're looking at a wide variety of applications for this technology. So that, you know, but the point being is that the ability to capture IP, to bring in other people's IP, to share that IP without sharing the actual core IP, and to be able to iterate at the pace of software on our hardware solutions, both mechanical and electronic. That's a game changer for us in being competitive in a large space. So.
Super. That's right. I'll take that. So Carl mentioned security. That really wasn't part of my other slides. I mentioned our two products, IntelliConnect's Fabric that we generate, and that's circuitry that goes into the implementations of the FPGA or the chips that we automate the creation of, and then Concertal, the web portal. But the third product that's in our, I should say we have a patent right now, but it's not part of our products that are deployed yet, is something called Secure Connects. Since we automate the chip workflow, if you will, from ideation all the way to the generated design, and we actually have hardware that we're putting into that design, we can represent that in a blockchain form. And so we can actually create certificates and tokens that basically provide assurances for each step along the way. And then we can represent those tokens in the hardware that we automatically generate that actually continue tracking the manufacturing flow, the test, the distribution, and once that part is in the field and deployed, someone can use those hardware features in order to authenticate the supply chain for that device. And with that single authentication that gets checked back to the blockchain, it's not just checking the device, it's checking the complete history of the device with everything that was used and all the IPs, regardless of where they came from, that can be certified along the way, basically give you basically an immediate authentication that you can trust that device, and we can use those tokens for protecting the data between devices also. So it's user-to-device authentication and automated security and automated device-to-device security features as well. So when you get into collaborative environments that are autonomous, devices will be able to automatically authenticate trust between this blockchain ledger, if you will, that's made publicly available. And then, well, we'll just move on. I'd like to, Ed, what time do we have to finish this one?
Officially 9 o'clock, but 9:10
Okay,
sometimes.
we have plenty of time. I'm not going to draw out the demonstration to be really long. But what we'll do is we'll log into our portal. You can access our portal through sda.concertal.com. By the way, I don't think Greg has put this up, but I think we can put this presentation material up on our microsite, iot.concertal.com, and you'll be able to get the presentation material if you want. So, and then these other links will be on there. But sda.concertal.com is where you can go to log into our portal, and then you have access to our Orchestrate SoC development environment. And once you're there, there's a little link on the bottom that says register an account. And basically you can do that and request login, and once you're there, you'll have a demo account where you can play with the system. And there's like a white paper-based design we can provide you additional information with, you can play with and things. We do all the development server side. You don't have to worry about installing any server or any software or whatever. And when you're ready to go to the back-end manufacturing floor or the implementation of an FPGA, let's say, we'll basically allow you to download that. Now that becomes a business relationship perhaps where we're actually delivering what we automatically generate. But to try it basically, just go on and do that. Actually, I didn't want to do that. What I want to do is go into the system here. Hey Greg, do you want to help drive here, by the way?
What do you need? Help with
He needs
that?
your help.
We'll just,
Man, happy to help.
well, so this site basically, we just logged in, and this is my dashboard. If you're, here's some recent IPs that I'm an owner of that I've been working on. And then down below are some designs. Let's just walk them through here, Greg. IP library. It's a place basically where you can just start browsing the IPs that are within our environment that you can have access to. Doesn't mean that you have access to it. These are just the IPs that IP providers have imported into the system that they can make available and that they've made visible. There could be IPs that are not on there also. If you have IP you've put up and you want to keep it private, it doesn't show up in the public catalog. And as you go through these categories and stuff, you can sort of see it, add the IPs you're interested in for your device to a quick list so you can reference them quickly later on. If you go to IP modules, the second, go to My IPs, Greg, or IP modules. Under here, if you want to import a new IP and make it automation ready and be able to mix and match that and build a system with other things in our environment, you can specify new IP and basically create a container for that and then start specifying the interface to that IP. And once that's done, you'll have a container where you can upload that, and then it's basically ready to be used in an automation build. Right now, we'll go to IP list. Under IP list, we'll go to My IP. My IP are the things I'm either an owner of or that I've been provided access to. And so let's just look at, let's say, the serial peripheral interface with the net protocol. So this is the documentation, basically a little bit of documentation of it, and so I can read a little bit more about that. It basically tells the status, the types of components that are there, that that you need to use. But if I go ahead and create the edit, basically, this is a tool that we call Audition, and this allows me to specify the interface. So when the IP is input to the system, I need to define the I/O pins for the IP, code modifying parameters that'll get passed down by the user of the IP in a chip level that they can modify. Design basically sinks and sources, which is data flow between the IP, wire events, which are like clocks or things that I might collect from a pin that I want to make available to other things in the system. Basically classes of information that I need to make available to a user of the IP. Anyway, once the IP is in, it's automation ready. So let's go over to design. My designs first. These are a bunch of designs that basically I have access to. Oh, by the way, we didn't show, but you can change the permissions in an IP owner and decide who gets access to that. Same thing for the designs, but these are designs that I own. When you go ahead and click on the green button for WP Design 1, if you sign up for a demo account, you'll have access to this design. And these are the IPs that are in there. There's a simple white paper that we can give you an overview of it. But basically, you can see it's basically a database representation of the functionality that's in the design. And so let's show you how easy it is to build a design. Let's just do something real simple. Go to Designs, Create New Design. Call it IoT Demo or something. And you'll see that you can start documenting it from a high level, but it'll also inherit the documentation from the IP that's in there. If you scroll down a little bit, you'll see that there's already one block that's here. It's called Handler. Handler is like our IntelliConnect's fabric that's going to glue everything together. It's got all the table stake stuff you need for a chip design. That's the clock control, the power management, some mode control registers for the guts of things, the self-arbitrating circuitry, so when you plug things in, basically it'll all work together. A debug port for debugging your design. Well, let's say I'm going to do a simple device. I want let's say an ARM M0 core. So we can add an IP to this design. Let's go down and add an ARM core. There you go. This is a simple microcontroller core. We'll just add one. We could add multiple cores if we want to, but we'll add that to the design. We're going to need, let's say, an SPI interface, something that users can talk to this chip on a board level with. One there. If you want to add multiple interfaces, we can do that as well. Let's say we're going to need some general purpose I/O pins. There's a 4-pin GPIO in here, I think. I think you passed it up there. Oh, there you go. So this adds 4 pins. This particular IP, if you were to go read the documentation, actually can operate those GPIO pins as pulse width modulators also. So we can use it as an output driver for a coil driver for Carl's motor, for instance, or it can be used as a sense input, perhaps, on a digital input signal. And you get the idea. You just add these IPs of everything you want. So let's go ahead and create that. Go down to the list, you'll see those added to the design. And I'm tethered on my phone right now, so things are working rather slowly. Oh, did you add those to the design? It's always dangerous doing a demo when we didn't talk about it. Did you hit the add button correctly? Okay.
Well, that's how we know it's real.
Yeah. Okay, well, you can do this yourself if you tie an account, rather than waste your time. And this, trust me, yeah, go ahead and add one. Okay. It's just you create. There you go. And I think he just forgot to add it. You get the idea. You add this stuff, and then on each IP, you can go in and you can further specify the interface to that IP through the Smart Connect or the IntelliConnect's interface and the relationships with other IP. Or you can just leave it blank. You don't have to do that for a first build if you don't want to. We'll just generate a highly configurable design on the connection fabric. So That's okay. What I want to do next is, so we're going to automatically generate a design. Someone's going to have to know how to use this. So hit the documentation button. And up at the top, you'll see there's design and test bench. If you select that, well, you can basically download the PDF document for your design. It's a user document for the device that we're going to create. When you specify the relationships between the IP, it's going to get automatically updated as well. Interesting thing is, we don't just create a design. We also will create a second design that's a test bench for it. So right out of the bat, we can compile these things together and allow you to interface with your part and to monitor it, basically, to start simulating. And so the documentation's all there, and then permissions, obviously, this is a web-based environment. So right now, Greg created this, but I'm the owner, but I can assign other people to be able to have access to this through the web browser. So we have a collaborative working environment now as well. So rather than, there you go. So let's go back to the dashboard a second, Greg. I just want to fast forward for them a moment. The dashboard, there you go. And let's just select the white paper design that they'll have access to. Or go ahead and just pick the IoT demo design there. Oh, no. Yeah, I think our bandwidth issue is an issue here. Okay, just go ahead and hit simulate design. And build it. This is actually the design that he just specified. So we specified everything in the database, and now what we're doing is actually executing our automated database-driven design flow. We're pulling the IP modules, the intellectual property modules he chose to use from configuration management. We're pulling those in. We're creating a fabric that functionally ties them together. Not just the wire connections, but our fabric is unique. It actually handles the operational aspects of how those collaborate together as a system as well. And we're customizing the adapters, the circuitry that goes between this fabric and the IPs, because that can be customized as well. He didn't specify anything, so we're going to basically create highly configurable adapters that the user will be able to program data flow and everything else in the chip. We're basically building all that, assembling the I/O ring and everything for it. We're also on the test bench doing the same thing. We're creating a second chip design, if you will, that can provide stimulus and monitor the I/O pins. Each of these designs have debug ports. So we'll be able to access the internal fabric and all the communication and monitoring with the IPs through these debug ports. What it means is the IP that we're using in designs, we basically have an architecture that allows you to automatically verify those IP in their integrated form in the final design. So we can actually allow you to do migration of verification test scripts for IP when they're used without having to go to a lot of these advanced technology that they're developing to solve those issues, just with standard tools. The build's complete. Do a refresh. Up on the upper left.
You always do that, you know.
Oh, but it's not showing on the build.
Yeah, I know. You always do that, but if you go here, it's right.
Okay. Yeah, so now we're simulating design. We've compiled all that together in a simulation module. Now we don't have any simulation scripts here at the moment. Let's go back, and if you can find the white paper one design, and just pull that up in the simulation. We'll just run a design, run a simulation to show you that it works. And as he does this, I mean, basically what he just did, he was able to build a documented working design with the functionality he needs in less time than it would take a product definer to write a functional market definition for a chip. Well, maybe not a market definition, but a functional idea basically. Hey, I have an idea for a product, can we go do this? We can allow you to start simulating that right now. Then you can go in here and you can allow it to start collaborating with others to actually tune and change that design and work together. It's a game changer. Not only that is, we've bypassed now the specification stage, the the detailed specifications are all inherited with the IP. Basically, the design team, we've actually started doing a lot of their work for them. If you want to use this just for a rapid prototyping platform, fine, just use it. If you want to use it for more than that and allow it to actually define your design team's chip architecture as well as it goes forward, we export standard RTL code that you can go through a traditional back-end flow with. So the point is we literally have eliminated weeks, if not months, and if you apply this to more complex design, perhaps years and man-years of collaborative effort that it takes to generate new designs. It is literally a game changer. So that's the big overview, I guess. And now he's simulating the white paper design. This just has a few scripts. If you go on, you'll be able to look at those scripts and see how you can exercise the design and stuff. So let's go back to, thanks, Greg. So that really concludes our presentation. What questions do you have? The people who are associated with Concertal are Kirk Otis, who's our new CEO now. Not officially, we're sort of need to actually formalize that, but as he said, he's having the business relationships, allows me to move over to CTO role. Greg, our systems and application support person. If you engage with us, he'll be able to help. Ed Bardwell has been a great advisor and is starting to help us with some of the digital content things. So we've got a lot of the team here. And then Carl, obviously, who's a partner, talked a little bit about what this means for him. We've got some proposals with his customers that we're working with. And even Ryan, who we've got a collaborative relationship on the machine learning side developing, is here. So that basically is the overview. So thanks for your time.
We're welcome to have a Q&A session here, so go right ahead, Brian.
What's your revenue model? Do you take a big check up front, or do you take royalties down the line?
Yeah, we're an early stage company. We have real product, real technology. So we're going to do whatever we can to get money in the company, obviously.
Okay, but the long run revenue model.
Yeah, so right now, I would, Kirk can talk about more of this. Early on, we're willing to do just a fixed price development. Pay us a fixed price based on the complexity of what you think your design is. We'll basically support you through the whole process of whatever it takes to get that through. We actually do customize an automatically generated fabric that ties everything together that becomes part of the design. So long-term wise, especially for volume parts, we'd like to move that towards a royalty model.
Right.
Sort of like what ARM does with their microcontrollers.
So if you need services, we can do that, but ultimately, the platform is a SaaS model.
Okay.
Yeah, so if we do it all up front now, that's
Yeah,
fine.
Not
We'd like
a
to,
license up front.
yeah, we'd like to
Okay.
go to a deferred revenue model that's a royalty based, and we can sort of gear shift that for whatever makes sense.
So royalty for the hardware, as well as you said a SaaS model, so you're charging per month or whatever to be able to
SaaS
use
model
that.
for the platform, there's a royalty model as you deliver product and chips go out with our IP on it.
Awesome.
Go ahead.
Well, just putting my lawyer hat on, if I am an IP owner and I'm sharing my IP with other people on your platform, that you've got some of your own IP, as the customer that goes to you and does this chip design, what do I get at the end of the day? What's my intellectual property? Because you've got yours, you've got potentially
Yeah,
third
great
parties.
question.
First off, you're only sharing it when you choose to share it.
Why would I choose to share my IP with somebody
Well,
without
because-
a royalty or?
Because you'll license it to them and then you'll get money for that.
So is
But
there a
you would
license
never
up
license
front?
your core intellectual property. You would never share your core intellectual property. It'd be sort of the stuff around it
So
that
part of the
other
way
people
is,
could reuse.
you're putting these containers up there,
Mhm.
but you as the IP owner have control of who gets to see that container. So say I wanted to use your technology, I would have to come to you. You could then in turn access on to me.
Right.
Now, one of the cool things about this is your IP is never exposed until the very output end. So you can do all these simulations and whatnot, and all of your IP is still kept on our servers that the customer never can see. They can see the output from the simulation, but they never actually see the IP. They never have the chance to get at it.
so they can play with it, work at it, and see that it actually does.
So
what
they
we
can,
want it to
you know,
do.
hey, we want to test out your IP to see if it works.
Exactly.
Which, you know, today, you know, usually you have to pay up front, and it's like, I really don't want this, but I had to shell out money to do that.
So is there a license
Yes, and
term to
has
try it
IP.
out?
So Ed
Somebody's-
has IP that he basically has put up on your system. Rob wants to use it. Rob asks Ed, he says, I think I want to use your IP. He exposes the capability of the module, but there's a license fee associated if he goes to production with it. Is that the model?
Right now, that's between these two people.
It's a
we're
marketplace.
out of that.
Oh, okay.
Yeah.
That's my primary concern.
So
Yeah,
we,
That's my,
so,
so I get to.
You control
And
your
no one
IP.
sees it
We
unless
say,
I
you
license
make an
it.
agreement, and then at the end of the day, you say, he has permission, and then when the output comes, you know, right now, eventually it'll be an automated check, but right now, we'll have to get something that says, you and him have agreed to whatever terms you agreed with.
It's not ours, it's not a shrink wrap. It's a specific license agreement.
Okay.
You make an agreement with him that says he can have your stuff, and then we can hand over the output.
So you turn it on when you have the agreement, and you can even turn on what level. Like for me, I would never let them see, like I'm gonna encrypt everything on my own hardware. So because I'm just gonna let them see, here's the input and output that you need for your application. I retain I license you to apply our design to our technology to your design, since we're building a robot. They can throw my modules in there, all they see is the input output. And they don't have access to the IP
to summarize, we've built the platform in a way that keeps all those relationships partitioned and the owner of IP in control if he gets to see it. Right now, a user of that IP has to work out an agreement with the IP owner before we will be allowed to export that to some chip developer.
So if I'm, you know, say I need a particular module or whatever, do I see that there's like 6 or 7 available, and so I know who to go to?
It's all up to the IP owner and what he opens up to be
okay.
viewed in the library. So, and so he can basically keep it totally hidden, just show that it exists in the catalog, allow people to actually try it in design, allow them to actually be a co-supporter of, you know, basically we can do customer support at a later date through our portal as well, because if you think about it, our portal is actually consolidating the relationships in the workflow. A lot of people, when they think of us just as an EDA tool. Oh, we're just some automation tool. But we're not. We're a single point where IP developers can go and put their IP to market their IP and to support their IP, for chip developers to see that and to use it. You know, even these containers that we're setting up, we've done it in a way that we could later allow an organization to extend their back-end flow activities into the process of the automation flow. And we could potentially open up revenue streams to be an IP broker if we wanted to. Like we could work out agreements for IP, you know, revenue basically models with the, and we could do a one-stop shop basically, and you get one bill for your chip based upon the criteria that's already been agreed upon. That's something we can develop into. We're not ready for that yet. We're worrying about the technology right now and to get those early stage customers. That's a good question.
Yeah, this may be kind of a nice question, but I'm working on a project right now where we're going to be taking a manual process.
Can we give her the microphone? Just one moment. My hearing is not as good as it used to be.
Yes, you want to.
Okay. I'm working on a project right now where we're taking a manual process and kind of dusting it off and bringing it out, and we'll be automating it. And I think security is going to be top-notch to us. So working on the business plan right now. What would I budget for customizing my own chip for this types of application? I like the blockchain part. What should I put in my budget that I'm doing right now for this
It really
piece?
depends. So it depends upon the complexity of the chip that they're going to be doing, the IPs that are going into it. So let's just separate third-party licensed IP from the equation, first of all, because every owner of IP is going to have their own requirements. Okay. But for our tools and our fabric, it really depends upon the complexity of the chip and basically the simulation features and the volume of product. I would estimate for the real simple designs, something on the order of, you know, if you have a half a dozen IPs that are all ready to go and it's not going to require a lot of support. If it was all up front, perhaps, you know, in the $30,000 to $50,000 range. If it's a really complex chip,
Should not be.
well, okay, well, but we'll talk and work with it. If it's just a, you know, we would even, for the right customer and to establish the right relationship, we could do something with some other creative revenue models as well.
Okay, great. We're starting to work on the business plan next week, so.
Yeah. When you apply it to the really more complex chips that might have several subsystems and, you know, let's say 30 to, let's say, hundreds of IPs and all that's required to make that, we're basically potentially eliminating millions of dollars of manual costs to get through the flow.
Okay.
And so it really depends upon the market and the support needed to do that. But what we'll stand by that, you know, as far as us being able to get you there at half the product cost is what our goal is. So,
Thank you. Appreciate that.
Kurt, did you want to add anything? I probably should have referenced you to that.
I got one over here. What you're doing is absolutely fascinating, and it reminds me of what LAMP did for Linux. I backed, I don't know how many Kickstarter projects of little system on chips that never came to light. I can only imagine there's a lot of plumbing that has to happen, and how do you wire all these modules before it goes into the die, and then what's the turnaround time?
Yeah, so that's the IntelliConnect's fabric that we automatically generate, a customized implementation of, based upon the database-driven design flow. And so that fabric basically has everything that's required to tie all this together. And to get into the details of that, we really have to go probably to an NDA, but it's sort of like a NOC. It's more than just a standard bus architecture like an ARM AMA bus, let's say, or an AXI or something. It's more than just that because it has methods of operation that are associated with it also that allow us to implement, if you want to get into it, like multi-agent operating systems that simplify the way things can collaboratively work together. And the interesting thing is this fabric functionality can extend into the firmware functionality of the embedded NPUs. So we can apply the same model to embedded software application code as well, even on multiple cores. And we can even demonstrate how we can do networking beyond a chip by extending IntelliConnects beyond the boundaries of the device. So as far as the overhead that's required to do the circuitry might be one thing that you're wondering. And all the overhead is really part of the database, and then it's customized and optimized for the implementation. So the overhead to build a chip with this flow compared to, let's say, a full custom design, engineering, sort of optimized fabric, if you will, you know, the overhead might just be a couple % or so.
Timeline, what are you looking at?
Oh, we just generated the full fabric right here for you, for a design. So it's basically, we can regenerate that. Normally, if in a normal design process, you go through and then late in the flow, you need to make a change, and all of a sudden has these ripple effect on design activities and stuff. With us, you just go back to the database. Oh, I needed an I2C interface instead of a spine. Boom. Change it, press the button, and regenerate. So you're ready to take that and bring it to a back-end flow.
Where does this get tested when you set it up? You know, it sounds good that piece is missing, but as someone outside the expertise, I'm not quite seeing, yeah, this thing's supposed to work with this other one, but what if it doesn't?
Right, so verification and validation is a huge part, right? In the normal flows today, there's a huge verification effort that goes on by IP developers to make sure things work before they're integrated into design. That's not always inheritable to the next step. With us, it's inheritable. So we help solve that issue so that chip designers using IP can reuse the verification scripts on the IP. So because of our methodology, the chances that you're going to have to change something in an IP in order to make it work with other things is solved. So once something is proven and verified, now you're not changing what's in that container anymore. because we basically eliminated the need to go in and modify that to make it work with other things. And then on the fabric itself, and then as the chip on the whole, there's verification methodologies like UVM, for instance, and stuff that build wrappers and can do constrained random test environments and stuff to allow you to exercise this stuff. We don't necessarily solve all those problems for our customers, but everything we do with our generated test bench can be part of accelerating that and what the things they need to do to make that testable. So I would say we help all that. Part of the value proposition we talked about in delivering the RTL, we didn't really talk about that, but there's extra value to be gained by the methodology and automation that we perform that basically has hooks into helping the highly manual processes that go on to do exactly what you're saying. In fact, verification can take over 60% today of validating a new chip design.
Yeah, so if you think about verification, one of the big problems right now is every new chip requires a new validation script or new test, right? If what we're doing, we're standardizing some of that, what you're getting output. So now you can start to standardize some of that verification and build in structures that are very repeatable. So now, it's still going to be custom, but maybe 50% of that is the same for every chip that you do. So, you have to put some allowances for changing some things, but we're giving out as a standard format structure, so you're kind of seeing the same thing every time.
So that's the simulation verification. Now you get into validation, like let's say pre-manufacturing validation of the design, maybe in real time so you can plug that into a real system. And FPGAs are used a lot by the design community to do those tasks. Typically, the simulation verification work and the FPGA emulation work to do validation on a pre-manufactured device are two totally different teams, two totally different environments, two totally different efforts, right? With the way we generate our test bench with a design, that test bench can actually be used for the test platform, for the validation FPGA environment as well. So the same scripts you use for simulation, now you can also reuse for your emulation environment. So we can accelerate that and remove a lot of the manual roadblocks, basically, that keep some teams from even considering doing FPGA emulation. Not only that, when you get silicon back, you have to validate those devices, right? You have to correlate them back to your simulation work, and I'm not even talking about the final test for manufacturing, just making sure it works before you go into the final test. The FPGA emulation stuff we do with that test bench can actually be used to test the devices when you get those back as well. So what we're about is not just automation. It's not just about an architecture. It's about doing all this and putting it together in a way that allows you to consolidate the efforts for a lot of the different aspects of a flow of what it takes to bring to market.
All right, last question.
A couple of questions actually. So this is for aluminum interconnect or for the copper?
Could you repeat the
I
question?
mean, the interconnectivity, the metal layers, is it for aluminum or copper?
It's whatever for a digital design, it's whatever the process technology is.
Okay.
It's for the integrated fabric, so it's not just the connections, it's the circuitry that functionally ties that together too.
Right. And the designs, are they flexible to change from technology, let's say from 0.6 to 0.4 micron technology, or is it, are you have to change every time you change the technology?
Yeah. Today we're demonstrating part of our products applying this to digital IP. And digital IP is typically transferable between different fab nodes. As long as the fab node, whether you're going up or down, supports the performance that you need to get from that block, right? So from a design flow problem, there's no issues. From a verification problem, there could be an issue, but that's dependent more on the IP requirements that were designed for, than anything else, and whether that'll transfer. So, but it's highly transferable. Now, our patent also teaches how to apply these principles to embedded firmware for microcontrollers, and that obviously, if you go to a more advanced process node, or let's say you have to move something down, or you're adding functionality and you basically start over-exercising what an NPU, a multi-processing unit can do. That's okay with us. You just add another core and take that and move it in, and you can distribute this stuff. And our Intelligent Connect works with the functional linkage, the functionality between cores, functions in different cores even, right? And it does that automatically from an architecture standpoint. We can also apply it to analog technology as well. We're not doing that today. I don't think we'll get to 100% automation on the analog side because there's things that you need to tune more that are more designer dependent and because of the customized layout things you have to do. But we can certainly get you, let's say 90% of it there, which is a lot better than what they do today.
Because at the end of the day, when you really launch the silicon, the SPICE models depend on the foundry would vary from, foundry
Absolutely.
to foundry, and the final speed and all the specs that come out. There is a lot of, gray areas. I was wondering.
Yeah, and on the digital side, those are, so part of what you're referring to is like timing, let's talk about the digital side, the timing closure you have to go through when you integrate this together, the dependencies between the different blocks and stuff, and how much effort's required to do that. So on the digital side, we've architected our fabric so all the IPs are cleanly partitioned and remain asynchronous to each other. And we take care of the timing relationships through the adapters that we build. What that allows us to do is, if you were timing clean in an IP on here and you had the timing closure scripts, you should be able to apply those easily to another process. If it doesn't work, it's up to that IP provider to support you with that. But it allows us to cleanly partition out and have a handle on the timing closure issues on the fabric, for instance, without having to worry about the interdependencies between all the stuff. So it's architected to simplify that and to put that in basically to really help the back end flow. And we can even extend automation to those tasks, but today we're stopping at RTL.
Okay, so let's call it quits for now, but you're gonna be able to stay later, right?
Yeah. So before I go, on the back table here, there's a one-page overview of the company. If you'd like that, take it with you. There's a little flyer that talks a little bit about the features and our product on the portal side. Got some business cards here, and yeah, we'll be around for a while, so stick around and talk.
Great. So you'll be able to stay. Carl, will you be able to stay for a while? Okay, and Kirk and all. So they'll be here. We have a room till 10:30 or so, or later. Stay and visit and network here. This is about finding each other and finding out what's going on in the marketplace. This has been a fascinating presentation today. Let's give him a hand, guys.